Okay, so in this problem, they say a pulsar is a rapidly rotating neutron star. We talked about neutron stars in the class. The Crab Nebula pulsar in the constellation Taurus has a period of 33 times 10 minus 3 seconds. So here's an object. Again, a neutron star is roughly, the radius of our sun is about 500,000 miles. It's a little less than 500,000 miles. And the mass of our sun is 2 times 10 to the power 30 kgs. So a neutron star is the size, the mass, same mass of our sun, except that it's 100,000 times smaller. So the radius of a neutron star is, let's say, 10 kilometers, something like that. Okay. And so here's an object from here to Ormond Beach. Its mass is 1,000,000 times that of the Earth. And it's spinning like crazy, and it's spinning in 30 milliseconds. One rotation in 30 milliseconds. That's what that number is telling me. It's crazy. And so there's the mass, 2.8 times 10 to the 30 kg. The pulsar's rotational period will increase over time. As it's rotating, it's emitting gravitational waves. Okay, so it's losing energy and it slows down. Okay. And the period will increase over time due to the release of electromagnetic radiation and gravitational energy as well, which doesn't change its radius, but it reduces its rotational energy. What is the angular momentum of the pulsar? Suppose the angular velocity decreases at the rate of 10 minus 14 radians per second square. What is the net torque on the pulsar? Okay. The angular momentum of the pulsar is I times omega. I for a sphere about its center of mass is that, and omega is it rotates 2 pi radians in its period. So that's the formula. Okay? So now we can put in all numbers. The mass is 2.8 into 10 to the power 30 kgs. The radius is 10 kilometers, 10 to the 4 meters. And period is 33.5 into 10 minus 3 seconds. Alright, so what we want to do is take care of powers of 10. So that's 10 to the 30, 10 to the 38, and then when that comes to the top, that becomes plus. So 38 plus 3 is 41. So 10 to the 41, and this is angular momentum, so kilograms meter square per second. And the rest of the stuff is 4 pi into 2.8 divided by 5 into 33.5. Okay, so that's what that works out to. There's that angular momentum. What is the angular momentum? Suppose the angular velocity is decreasing at a rate of, what is the torque on the pulsar? Okay, so part B, torque is dl by dt. Okay, and d by dt of I omega, and the moment of inertia is not changing, so d omega by dt I times alpha. Okay. And so torque is I times, oh, I should have calculated I separately. Oh well. D omega by dt is 10 minus 14 radians per second squared. Okay. I did a mistake. Well, anyway. So that's what this is. And again, let's take care of powers of 10, 30, 38, minus 14, 24. Okay. And torque, so this will work out to be Newton meter. Okay. All right.